Hello everyone. Today we'll learn about Lagrange multipliers and Lagrange formulation of the equation for optimization. Let's first understand the motivation behind studying the Lagrangian formulation. Suppose you have a function f of x is equal to minus 3 plus 2 times x minus 4 the whole square, and you have to find the minimum value of this function. The conventional method is to differentiate the function and then equate it to 0 to get the critical value. Here the critical value is x is equal to 4. You can see that I have differentiated the equation. I got this equation. Equating that equation to 0 gives me x is equal to 4. Now the value of the function at x is equal to 4 is the global minimum, as you can see in this diagram. However, when you place constraints on the above function, the minimum value changes subject to the constraint. If you impose the constraint that x is greater than or equals to 5.2, then the critical value becomes 5.2, and then the minimum value of the function then becomes f of 5.2. Thus we can't use the traditional calculus methods here to find the minimum value of the function, because adding more constraints makes it more complex to solve. This is where the Lagrangian formulation comes into picture. The Lagrangian formulation comes into picture because Lagrangian L takes the constraints into consideration when formulating the objective function, and the advantage of this is this formulation helps in applying traditional calculus methods. This is the main motivation behind studying the Lagrangian formulation. Now we know the importance of Lagrange formulation. Let's understand the mathematical definition of it. So the theorem is, let f and g of I be continuously differentiable on an open set X contained in R. So that means where f is the objective function which we want to maximize or minimize, and g of I are the constraint functions. So let f and g of I be continuously differentiable on an open set X contained in Rn. Suppose that x0 is a local maximum point for all the x belonging to the neighborhood of x, such that in that neighborhood g of I is also satisfied. Also assume that the Jacobian matrix of G has the rank of M. Then there exists a unique vector of real numbers lambda 0 called multipliers, such that the derivative of f with respect to x at x0 is equal to sum product of derivative of g with respect to x at x0, and this sum product is with respect to lambda, and this lambda is called as Lagrange multiplier. I know this is a lot, but let's go step by step. Let's try to understand what each word means. There are few important points to remember from this definition. There are few assumptions, such as f and g are continuously differentiable. The second assumption is m is less than n. That means the number of constraints are less than the number of variables. The third assumption is x0 is a local maximum point of f. This x0 is a local maximum point. The fourth assumption is the Jacobian matrix of G with respect to x has full rank M. If all the assumptions are true, then we can say that the derivative of f with respect to x at x0 is equal to sum product of the derivative of g with respect to x at x0. Remember that even though the equation of the Lagrangian multiplier involves the first derivative, f of x means the meaning is this equation is in terms of the differentiation operators. So remember that even though this equation number 1 involves the first derivative of the functions. Here, the Lagrangian equation for optimization, which is this equation number 2, it is not made up of derivatives. Instead, it is a linear combination of the original objective function and again the sum product of constraints along with multipliers, this one. So remember that this equation has derivatives, whereas the original equation for the Lagrangian optimization that doesn't contain any derivatives, where lambda I is again Lagrange multiplier. Let's try to understand this from geometric point of view. We'll understand the mathematical definition much better if you understand the geometric intuition behind Lagrange multiplier. In the diagram, f of x is a multivariate function and the counter lines represent level curves. These lines represents level curves. You can think of these curves as obtained after cutting a 3D graph at a certain level. Here g of x is the constraint function. The point at which they will meet will have a common tangent at this point. You can see the common tangent in the diagram, this. Now perpendicular vectors to that common tangent, these two vectors will be in opposite direction, and these perpendicular vectors are nothing but the gradient vectors of f and g, because of the property that gradients are orthogonal to level curves. We will see shortly why these two vectors are the gradient vectors of the functions and why they are perpendicular to the level curve. For now, we know that if two vectors are perpendicular to the same tangent vector in this way, then they will be parallel and scalar multiple of each other. This scalar multiple is called as the Lagrange multiplier. Thus we can see in this equation why their first derivatives are equated. The negative sign here is only to bring the two gradient vectors in the same direction. Now the question is, how do we know that these two perpendicular vectors which are perpendicular to the same common tangent are gradient vectors? To understand that, let's revise some basic undergraduate calculus. If you don't want to revise, you can skip this section and directly start with the section where I am connecting all the concepts and solving an example. This section. Back to the Lagrangian formulation. So let's quickly go over some undergraduate calculus concepts. Partial derivative means differentiating with respect to one variable while keeping other variables constant. For example, when you differentiate a function of x and y, so when you differentiate it with respect to x, you treat y as constant, and similarly when you differentiate it with y, you treat x as constant. The second concept is, if del by del x1 of f of x is greater than 0, then to increase the value of that function, we move along in the direction of increasing the value of the variable. Okay, what this means is that if you have a function f of x and you differentiate that function with respect to one variable, and if that is positive, then to increase the value of the function, you know that to increase the value of this function, you have to move in the direction of increasing x1. Similarly, if you differentiate the function with respect to x1 and if that is negative, then to increase the value of the function f of x overall, you move in the direction of decreasing x. You will understand this from this diagram. We all know this is a diagram of y is equal to x square. The differentiation of the function at this point will be 2x. So the derivative at this point will be positive. That means to increase the value of function we have to go in the direction of increasing x, which is this direction as shown in the diagram. Similarly, the differentiation at x is equal to -1, which is this point, the derivative is negative. That means to increase the value of function overall, we have to go in the direction of decreasing x, which is this direction. So that's what these two concepts are related about. The third one, the derivative of the function with respect to x1, if it is equal to 0, then that point corresponds to either local minima or maxima, or in the case of multivariate function, it corresponds to saddle point, which we'll study soon. The next property is very important, which says the direction of the gradient is equal to the direction of the steepest ascent. Now this is very important property, and this is always true. Direction of the gradient is always equal to the direction of the steepest ascent. So what this means is, let's like this example. Here the direction of the gradient at this point is towards the right. What that means is the direction of the gradient point towards the direction of the steepest ascent. That means for the function to increase by a large value, like to have the steepest ascent, the x has to increase in this direction. And similarly, if the function is at this point, and we know that the derivative is negative at this point, then to increase the value of the function by the steepest value or by like the maximum value possible, the function has to travel in this direction. That is, the x has to travel in this direction. So this was the case for one variable. Suppose we have more than one variable. In this case, here we can go in more than, like here we can go along the axis, such as this x-axis, this y-axis and z-axis. Along with these directions, we can also, there are so many directions, like this direction, there are so many directions. So which direction will give us the steepest ascent, or the direction in which if we move, we should be able to get the highest value of f of x possible for that increase. So to get that direction, we know that direction of the gradient gives us the direction of steepest ascent. So the four arrows which you see, the small arrows, these are the arrows of the direction of the gradient or direction of the steepest ascent. Now this property is very useful. We'll see how this plays an important role in the derivation or in the geometric intuition of Lagrange. The next is just the mathematical formulation of the gradient of a multivariate function. This is just a brief review. Now the next is, we know that gradient points in the direction of steepest ascent. We just saw all these small arrows, they point in the direction of the steepest ascent. Therefore, gradient of a multivariate function gives the direction of the steepest ascent. Okay, we know that. To find out arbitrary directions rate of change. Okay, we know that gradient gives us the direction of the steepest ascent, but if we want to find what will be the rate of change in any arbitrary direction, how do we do that, or how do we find out? Okay, let's continue to read. To find out arbitrary directions rate of change, not just limited to orthogonal or steepest ascent directions, we use directional gradient. And the definition of directional gradient is the gradient of the function multiplied by a unit vector in the direction for which we want to find out the rate of change. So this u bar is a unit vector, and del of f is a gradient of f at x0, y0. The next concept is the dot product. U dot v is equal to norm of u multiplied by norm of v multiplied by cos theta, where theta is the angle between the two vectors. And we know that the dot product is 0. That means the angle between the two vectors is 90 degree. The next property is, consider a set of vectors v1, v2, v3 till vn. The span of those vectors will be the linear combination of those vectors. Now why are we studying this property? Because this is related to the span of constraint functions. We are looking for solution in the span of constraint functions. You can see here in this definition of Lagrange, lambda multiplied by gi of x and summation of those values for from 1 to m, that is nothing but the span of the constraint functions. Moving ahead, this is the mathematical formulation of the Jacobian matrix of G, and we want, and the assumption for this, like why are we studying this? Because we had assumed that the matrix is invertible. Why is it invertible? Because we are assuming that it has full rank. And why do we assume these two things? Because we want that there should be no redundancy in constraint functions. That means one equation cannot be written in terms of another. So using all these concepts, we can easily explain that gradients are orthogonal to level curves. Once you have understood the concepts, now let's see how everything connects. Consider a function f of xy. F of xy is equal to sine of root of x square plus y square. This is the 3D diagram of the function. Now if you cut this function by a plane which is parallel to x-axis and x and y axis, suppose if you cut the function at this point and if you project the points, then you will get this diagram. And for this particular level, the z value is fixed. So for a level curve, even though x and y changes, the value of z will stay the same. That's why it is called a level curve, because it is at a level. You can imagine the level curve as the counter plot of a mountain. If you move along the counter lines of a mountain, you will still be on the same elevation. Okay. When you cut the above graph by a plane parallel to xy plane at some particular value of c and project the top view on xy plane, then you get level curve. Okay, fine. Now let's calculate the gradient of the function. Now this is the gradient of the function, and we know if we substitute the values of x0 and y0, suppose, then this gradient will give us the direction of the steepest ascent. The above gradient gives us the direction of the steepest ascent, that is the direction for increasing the value of f by the maximum amount. But to find the arbitrary direction's rate of change, we can use directional gradient, and directional gradient is gradient of the function multiplied by unit vector in the direction for which we want to find out. Now suppose there will be a direction where this gradient vector will equate to 0. That means the dot product of the gradient and the unit vector will equal to 0, and that is possible when the angle between them is 90 degree. That means when the directional gradient is 0, the rate of change for that arbitrary direction is 0. This is possible only on a level curve for a function, because as we just saw, on a level curve x and y can vary, but the value of z will stay the same, that is the value of c will stay the same. So this is possible on a level curve, as you can travel on a level curve without changing x and y, without changing c values. Yes. And how will you travel in the, so thus when you travel on a tangential vector at any point on a level curve, there is no change in f of x and y. The gradient of a function and the dot product with the tangent vector is equal to 0, which is equivalent to saying the gradient of the function means direction of maximum change, and the tangent vector of the function means direction of no change. So this is by default, by logic, this should give answer as 0. Now again coming back to the diagram, these level curves called the counter curves, when they meet the constraint function, like this level curves of the objective function, they meet the constraint function, they meet at a point, we have the common tangent, and the normal to that tangent will be the directional gradient of the objective function and constraint function, which is the derivative of the function is equal to, as we know that this is a multiplier. Why it will be multiplier? Because these two are parallel to the these two are perpendicular to the same line, so that's why they will be parallel and scalar multiple, as we have already established the intuition behind Lagrange multiplier. Thus we have established the geometric and mathematical intuition of the Lagrange multipliers. Now let's consider a very easy solved example. Suppose we have a function f of xy is equal to xy, which we have to maximize such that g1 of x is equal to x plus y minus 10 is equal to 0. Now the Lagrangian formulation L of x, y, lambda, this is how you write the Lagrangian L. F of x comma y plus lambda 1 g1 of x comma y minus 0, which is this one. Now finding the stationary points of the above function. Finding the stationary points of the above function, we know that we can either get a saddle point for multivariate function or local maxima or local minima for one variable. So let's do the partial derivative. With respect to x, you equate to 0, you get y is equal to minus lambda 1. When you differentiate with respect to y and equate to 0, you get x is equal to minus lambda 1. When you differentiate with respect to lambda and equate to 0, you get x plus y is equal to 10. Now using this, all the three equations, you can easily reach this solution stage, that is x is equal to y is equal to 5 and lambda 1 is equal to minus 5. Now to calculate whether it is maxima or minima or saddle point, we have to find Hessian matrix. Now that is not part of this video, but now we have understood what is the intuition behind Lagrange multiplier and what is the importance of Lagrange multiplier. Now this is not the end. Many of the times you will often see Lagrange multiplier accompanied with KKT conditions. KKT conditions. In the next video, we'll study how these conditions along with the Lagrange multiplier can be used to solve nonlinear optimization problems. That's it for today.